So hey everybody, this is Amr Abdulbaki and my colleague here Ali Isa. We are going to present to you our final presentation of our project, which is descriptive image captioner. Let's start off with the baseline model that was deployed in Milestone 1. It's a basic encoder-decoder architecture, and the encoder was a ResNet 152 with convolutional neural networks with linear layer, and the decoder was a long short-term memory RNN decoder. The dataset that was used was Microsoft Common Objects in Context, and the input to the model was basically an image, and the output was a caption for that image in a very simple manner. Moving on to the final model, which we have reached now, it's not so different, but it's also very different at the same way, where it also has the encoder, there is a 152 CNN with a linear layer, and the decoder along short-term memory RNN and linear layers as well. We implemented a temperature input here, as you can see. It's inserted into a vector of features, which is combined. It's combined with a vector of features, which is the output of the CNN encoder, as you can see from the diagram. And then it's given to the long short-term memory decoder, which is a one-to-many. So it takes this vector and it moves it above a linear layer, and according to the value of the temperature, it will provide as much detail as possible to the sentence. Where if the temperature is close to 0, it will ignore some details, but if it's closer to 1, it will extract more details. As you can see in the output here, this is the temperature of 0.9. It provided a huge output. With another output that is less than 0.9, it will provide a much lesser output. And what was actually implemented during this whole project? Well, we started by deploying the baseline model. Then we used two different datasets, which is visual genome version descriptions and image sequence descriptions. We performed data augmentation techniques on these two datasets to support this new temperature feature using importance scoring and other functions from the NLTK library in the Python. We also added the temperature as an input to the decoder, and after adding, as we discussed before in the feature vector, so we also experimented with a blue decoder, a gated recurrent unit, a long short-term memory decoder with soft attention, and a solo transformer as a decoder with a newly added temperature as well. We also experimented with a pre-trained embedding called the Globe 6P of 300 dimension to enhance the training process. And we noticed that there was a little bit of a repetition in our captions. So we decided to add a repetition penalty on the last milestone in order to the loss function in order to penalize the repetition of some words or whole sentences in the output. And of course, we trained with different hyperparameters, number of epoch optimizers and learning rates, safety weights to trace which model is better. And now we'll move on to the demo time, as one might say.
Okay, so now we have this collab here. Here we have our model with the with the pre-trained weights and the pre-trained embedding. Here we can choose a certain temperature, let's say 0.9, and this is the image it's going to do the inference on. See a man who's wearing a red t-shirt, brown shoes, and such. If we reduce it to something like 0.2, and the output is shorter. And we can also try it with a different image like this, for example. And it thinks it's this is a cow. So, yeah. Okay, so starting off, the challenges we faced during this project, which are very, I mean, they seem very few here, but they're very drastic in my opinion. Which firstly was finding the data sets which have the long descriptions of diverse images, which will enable us to do the temp variation of the different lengths of descriptions. Obtaining captions for assessment during the training for the RNN with self-attention. So this milestone focused on trying different decoder architectures. One of them was the RNN with self-attention, and we've had difficulty obtaining the sentence, the inference sentences while training, because we were using PyTorch and we have had difficulty with tensor sizes and reassembling the sentence and so on during training. So we've had difficulty having metrics for it during training. And we've also had sort of the opposite of that for the transformer decoder. So we've successfully enabled it to train, and we've had actually a pretty high accuracy during training, but and we can do the inference or reassemble the sentences during training, but we've still having issues with sampling with just regular sampling outside of training, because refeeding the input into the decoder many times and concatenating and such, and also training time, obviously. So the conclusions are we've been able to train on the temp descriptiveness parameter successfully. We've been able to explore new data augmentation techniques and methods to support this new feature. We attempted to enhance the baseline model by integrating more modern architectures like GRU, soft self-attention, and the transformer decoder. The transformer model and RNN model seem the most promising, and we intend to do the potential for further development on them. But sadly, due to the difficulties on them, we didn't have the sufficient results for them to be the final model that we end up with. Now, the final model we've chosen is the RNN with the pre-trained embeddings, because it achieved a Blair score of 0.053 on a validation dataset of 150 images. That is as compared to 0.005 with the RNN with self-attention. But again, the one with the pre-trained embedding had 80 epochs to train on, and the one with self-attention only had 15. So for the future plans, we plan to explore more with the transformer decoder, because we've noticed that actually it was able to learn very quickly and almost memorized the entire dataset in less than 15 epochs. We intend to experiment with having a pre-trained embedding plus, in addition to one of our decoders, like the self-attention. We still haven't played around with different sizes of our hidden layers, and possibly more LSTM layers, for example. And we need more data sets also for generalization to different applications. And these are team member contributions over all of our projects. And thank you for listening.